to the video lectures for Math 141 Statistics at Morton College. Once again, I am your instructor, Dr. Scott Spaniel, and here today we're going to start Chapter 11 with Section 11.1. So, Chapter 11 is a nice build off of Chapters 9 and 10. In Chapters 9 and 10, we looked at doing confidence intervals and hypothesis testings with one set of data. So in confidence intervals, we were simply looking for where is the to make a region where we think the population proportion is, and in chapter 10, we were doing hypothesis tests where we compared sample data to a value predetermined, either something from the past or the majority or something like that. In 11.2, what we're going to do is we're going to compare two samples to each other. We're going to compare two groups to one another. And these groups can either be dependent or independent. So that's what we're going to start off with, is reminding ourselves what is the difference between independent and dependent. So if you take out your Chapter 11 note sheets, you can follow along. Once again, just like with all the other videos, those note sheets can be found either in Blackboard or on my math lab, depending on how I set your course up. So here we go on page number 2. So a sampling method is independent when the individuals selected for one sample do not dictate which individuals are to be in the second sample. A sampling method is dependent when the individuals selected to be in one sample are used to determine the individuals in the second sample. Dependent samples are often called matched pairs samples, and it is possible for a person to be matched against him or herself. Okay, so let's look at some examples to see if we can pick out the difference between independent and dependent. So a political scientist wants to know how a random sample of 18 to 25-year-olds feel about Democrats and Republicans in Congress. She obtains a random sample of 1,030 registered voters, 18 to 25 years old, and asks, do you have a favorable or unfavorable rotated opinion of Democrats, Republican rotated party? Each individual was asked to disclose his or her opinion about both parties. Okay. So the question here is, what are the two samples? Well, here they said they only asked one random sample of 18 to 25-year-olds. So that makes you think, well, are there two samples? But the key here is that they were asked to disclose his or her opinion about each party. So this is an example of a person getting paired against themselves. Okay, so this falls under matched pairs, which means this is dependent. Okay, because they were matched against themselves. So that the authors of this study could compare, the political scientists could compare the opinions of the Democratic and Republican Party amongst individuals. So to see what the difference was for individual people and then find that out as a group. So the next one, an educator wants to determine whether a new curriculum significantly improves standardized test scores for third grade students. She randomly divides 80 third graders into two groups. Group 1 is taught using the new curriculum. Group 2 is taught using the traditional curriculum. At the end of the school year, both groups are given a standardized test and the mean scores are compared. So the question here is, we definitely have two groups. So that means this could be independent or dependent. But the question is, did who was in group 1 determine who was in group 2? And the answer to that is no. So this would be independent. Even though, if you're in one group, you can't be in the other one. That didn't determine. We didn't say, well, we're going to take one kid for group 1, and then this is the reason why we're going to take this other kid and put them in group 2. There was no pairing up. So that's independent. So we got two more here. So go and pause the video for a second and try these on your own and see if you can figure out which ones you think are either independent or dependent. Okay, so the first one, a researcher wishes to determine the effects of alcohol on people's reaction time to a stimulus. She randomly divides 100 people aged 21 or older into two groups. Group 1 is asked to drink 3 ounces of alcohol, while group 2 drinks a placebo. Both drinks taste the same, so the individuals in the study do not know which group they belong to. 30 minutes after, is what that word should say instead of age, after consuming the drink, the individuals in each group perform a series of tests meant to measure reaction time. So once again, she randomly put these people in these two groups, so this is independent, similar to the one above. Right? There's no connection between the two groups other than they came from the same big group. So that's independent. And then the last one, a sociologist, which is compare annual salaries of married couples in which both spouses work and determine each spouse's annual salary. So the key here is that the two groups are connected because they're married couples. So that's dependent. They're matched together, in this case through marriage. Okay. So this independent versus dependent thing is going to be important here because it's going to help us decide what technique we need to use in order to do the hypothesis test or confidence interval we're looking for. So the first set of these we're going to look at here in 11.1 is inferences for two population proportions with independent samples. So these are samples like the students in the classes or the people drinking, the reaction times. Those were both examples that might fall under this, although those were both means, so they wouldn't fall exactly under this. So let's go ahead and try a problem here. So in many colleges and universities around the country, educators are changing their approach to instruction from teacher/lecture-centered model to what this class actually is, which is more of a student-centered model, where students learn in a laboratory environment, which students can proceed at a pace suitable to their learning needs, and lecture is de-emphasized. In one school where this model was being introduced, of the 743 students who enrolled in the traditional lecture, 364 passed. Of the 567 in the student-centered model, 335 passed. So first off here is we can notice that this is independent because there's no relationship between the two groups. Okay, you just had a bunch of students who took the traditional model and a bunch of students who took the student-centered model. So in this case, what is the response variable and what is the explanatory variable? So remember, the response variable is the variable that is responding to the explanatory variable. So in this case, the variable that is the response is whether or not they pass. So the pass rates is the response variable. And then the explanatory variable is the teaching method. Okay. And looking back on how I made this note sheet, I'm definitely going to have to change in the future because I gave you a bunch of space to answer that really question, and then we can skip down here. So does the evidence suggest that a student-centered model results in higher pass rates than the traditional model? Okay. So what we're going to do here is we're going to do hypothesis tests just like we did it in the previous chapters, but with a fairly small but significant difference, which is in this case, I'm not comparing a p-value here. I'll write up here a p-value to some fixed number, right? So to some number, and then I'm not doing so. Then p is that would be my h1, and then my h naught, and then my h1 is that p. Let's just say does not equal that same number. What we're going to do instead, so let's just give that name A, for example. What we're going to do instead is we want to compare h naught of 1p. Are they equal to h of p1 and p2 to h1 of p1 does not equal p2? Or p1 is less than p2? Or p1 is greater than p2? Okay, so we want to compare these numbers directly. So it says, does the evidence suggest that the student-centered model results in higher pass rates than the traditional model? So let's get all the information we have in this problem, right? So what we've got is, and let's set it up. So we've got traditional, and we've got student-centered. Okay, so for traditional, we've got an N of 743 and 364 passed. So N is 743 and X is 364. And for student-centered, we've got 567 took it and 335 passed. So N equals 567 and X equals 335. Okay. So now what we want to do is we want to set up our hypothesis. Okay, so our hypotheses, we're still going to have two of them, just like we did in Chapter 10. And one option is going to be that they're equal to each other. So we could have the proportion of that passed of the traditional, so P sub T is equal to the proportion that passed the student-centered. And then what we want to do for the alternative, so we want to say one option is they're equal. For the other hypothesis, we want to put the one we think happened. So in this case, it says, does evidence suggest that the student-centered model results in higher pass rate? Okay, so the question is, which way does the inequality go? Well, we want traditional and student-centered. We want traditional to be smaller, so we want traditional to be less than student-centered. So we're going to do the less than. Notice in this case, in chapter 10, this inequality would always go the same way no matter who was doing the problem, right? Because we were comparing it to a fixed number. But in this case, it matters which way you write the hypotheses, because I could have alternatively written the hypotheses like this, right? I could have done P, put the student-centered on the left. And if that's the case, I still want student-centered to be greater. So we would have to do a greater than symbol. So depending on which side you put the proportions on changes the way you write the second hypothesis. So two of you could be doing exactly the same problem, but if you flipped which proportion goes on the left or the right, you might have a different inequality, which will change slightly how this goes into the calculator. Okay. So now what we're doing is we're doing a hypothesis with proportions, and we have two samples. So if we go into our calculator here and go into stat and test, right? That's where we would expect the hypothesis test to be. Now we're doing a proportion. We're doing a test. So you might expect us to be doing one prop z-test, right? That's the one there. But instead of having one sample, we have two. So we want to use two prop z-test. So we're going to choose two prop z-test for this problem. So I'm just going to write that in the notes real quick. Okay. And notice if I go ahead and bring up a one prop z-test below it, you'll see that these are exactly the same, right? Except in like same basic idea, but instead of P naught, we don't have a P naught, right? Because we're comparing, we don't have a fixed value that we're comparing our sample data to. We're comparing two samples. So instead of having a P naught value and an X sub n and an X and an N, the value of the null hypothesis, the sample of success count, and the sample size, instead what we get is we just have our sample success count for the first sample with the first sample size, the sample success count in the second sample, and the second sample size. So I'm just going to put in here my values. So our for our X for traditional was 364. Our N for traditional was 743. Our X for student center was 335. And our N for student center was 567. And so what you should notice here is it gives us test statistic. It gives us the p-hat values for both samples. So the pass rate for sample 1 was 49%, and the pass rate for sample 2 was 59%. And then it gives us our 3 p-values, and you have to pick the one that matches your sample. So in this case, we were doing this one right here, right? We were doing less than was the one we chose to do. So that means our p-value is p equals 0.0001. Okay, so that's the p-value we got from the calculator. And so we want to compare that to alpha, just like in chapter 10. So is that less than alpha? In this case, yes, it is, right? That's less than 0.05. And so that allows us to do exactly the same thing we did in the last one, which is reject H naught. So we're rejecting the fact that they're the same, and so now we can write the alternative hypothesis. Okay? And so in this case, we can write there is sufficient evidence to suggest the student-centered model results in higher test scores. Okay. So that's the idea. So this works just like it did in chapter 10. The only thing that's a little different is that instead of comparing P to some fixed proportion, we're comparing two different p-values. Okay. So let's go ahead and flip to the next page, and we can try one more of these together, and then I'll have you all try one. Okay. So in October 1947, the Gallup organization surveyed 1,100 adult Americans and asked, are you a total abstainer from or do you occasionally consume alcoholic beverages? Of the 1,100 adults surveyed, 407 indicated that they were total abstainers, so they never drank alcohol. In July 2010, the same question was asked of 1,100 adult Americans, and 303 indicated that they were total abstainers. Has the proportion of adult Americans who totally abstained from alcohol changed? Okay, so in this case, we've got 1947 and we've got 2010 are our two groups. And we've got our X and our N for both. Our X for 1947 is 407 and our N was 1100. And for 2010, our X was 333, and our N was 1100. Okay. Now in this case, we don't have letters we can use, so I'm going to call this one on the left, this group 1, and we'll call this one on the right group 2. So when we go to write our hypotheses, we're going to have our H naught and our H1, and we're going to have P sub 1 and P sub 2. And just like in chapter 10, your null hypothesis is always that they're equal. And then your alternative hypothesis is based on what you're trying to prove. In this case, we're trying to show that it changed. So when we see the word change, that means we're going to use not equal to. So if I want to know just has it changed, then we don't care which direction it's gone. All we care is it changed. So we're going to use not equal to. Okay, and so now that's all the information we need in order to do our hypothesis test, right? The information we need are these X values and N values for group 1, the X value and the N value for group 2, and which direction or two-tailed is our hypothesis. So now we can go into the calculator and we can do 2 prop Z test, and the shortcut for that is just these capital letters TPZT. If you don't want to go to the menu, you can just type in TPZT. And then we can put in our value. So X for the first group was 407 out of 1100 total. And for the second group, it was 333 out of 1100 total. And so over here on the right is our not equal to value. Okay, so that's the one we're going to use. So in this case, our P value is not equal to, so 0.00084 if you want to add another, but 0.0008 is plenty low. Okay. So the question is that less than alpha? Alpha was 0.05, so yes, it is. So we can reject H naught, and we can write a statement affirming the alternative hypothesis. So there is sufficient evidence to suggest the proportion of Americans who are total abstainers has changed since 1947. Okay. And on the homework or the quiz, most likely, or the test, you'll just be doing multiple choice if you're doing those things online, so you'll just choose the right conclusion. That's something like that. If this were a handwritten test, you would need to write something like this out. And just remember, just like in chapter 10, we don't want to say it proves anything because this is still just sample data, but we have enough evidence to strongly suggest that it has changed. Okay, so that's the idea. So what I'd like you all to do now is pause the video for a second and try doing this problem on your own, and then when you hit play, we'll go through it together. Okay, so now you've had a chance to try this. Let's go through it together. So the drug Prevnar is a vaccine meant to prevent certain types of bacterial meningitis. It is typically administered to infants starting around 2 months of age. In randomized double-blind clinical trials of Prevnar, infants were randomly divided into 2 groups. Subjects in Group 1 received Prevnar, while subjects in Group 2 received a control vaccine. After the second dose, 137 of 452 subjects in the experimental group, Group 1, experienced drowsiness as a side effect. After the second dose, 31 of 99 subjects in the control group, Group 2, experienced drowsiness. Does the evidence suggest that a lower proportion of subjects in Group 1 experienced drowsiness as a side effect than in Group 2? So lower proportion. Okay, so we've got our Group 1, right, which is the experimental group. Their X value was 137 out of a total of 452. And then we've got our group 2, which is the control group. Had an X value of 31 out of 99 total subjects. And then our hypothesis is, are their proportions the same? So is the proportion in group 1 equal to group 2, right? That's always your null hypothesis. And then our alternative hypothesis is that the proportion was lower for group 1 than for group 2, which is not what I wrote. Sorry, is lower, so that means we're going to do less than, right? And once again, if you had flipped these groups, then it would be greater than. The key is you want group 1 to be on the pointy side of the inequality. You want group 1 to be the smaller value, which is always on the pointy side of the inequality. Whichever side of the inequality you root group 1. Okay, so in this case, we're going to do less than. And so now we're ready to do our hypothesis test, right? Because we've got our X and N for both groups, and we've got our inequality, which in our setup is less than. So I'm going to do a 2 prop Z test. Once again, TPZT is the shortcut to get to this, and I can put in my value. So 137 out of 452 and 31 out of 99. And so in this case, for less than, over here on the left, our p-value is 0.4221. Okay, and that's all we need from the calculator is that p-value. So now we can go back to our notes and ask, is that less than alpha? And the answer to that is no. So we do not, just like in chapter 10, we do not reject H naught when the null when p is not less than alpha. And so now we can write a statement saying there's not enough evidence for the alternative hypothesis. So there is not sufficient evidence to suggest a lower proportion of subjects experience in group 1, experienced drowsiness compared to group 2. Okay. And so that's all there is to that. So as I said at the beginning, this is pretty similar to what we were doing in chapter 10. But the only big difference is you're comparing two different groups instead of a group to a fixed number. And that's where the changes come in and how we do the hypothesis test. But the setup of doing a hypothesis test is exactly the same. Still write our hypothesis, still do the test, still reject or do not reject H naught, and still write a conclusion. Okay. We can also, which I left here something from our calculator, but we can do a confidence interval. Okay? In a similar way to what we did. And we are going to use, in fact, the same command as you would use in a calculator, which is 2 prop z int. Okay? So that's what we can do. So we can try doing a confidence interval the same way, just like in chapter 9, but we can look at it. So the Harris poll conducted a survey in which they asked, how many tattoos do you currently have on your body? Of 1,205 males, 181 reported they had at least one tattoo. Of 1,097 females, 143 responded that they had at least one tattoo. Construct a 95% confidence interval to judge whether the proportion of males that have at least one tattoo is significantly different, is the word I left out of there, different, from the proportion of females that have at least one tattoo. Interpret the interval. Okay, so we can make an interval using that information. So just like what we've got before, we've got males. We have X is 181 out of a total of 1,205 males. And for females, we've got an X of 143 out of a total of 1,097 females. Okay, and we're going to do what I underlined up there, which is 2 prop z int. Let me get rid of these. So if I go into my menu under stat tests, I've got 2 prop z int down here at the bottom, just like I had 2 prop z test. And it's going to look just like 1 prop z int, except we're going to have 2 samples to put in. So we've got x sub 1, n sub 1, and so on. And the shorthand to get this is TPZI. Yeah, so TPZI gets you an interval if you want the keyboard shorthand. So male, our first group was 181 out of 1205. Our second group was 143 out of 1097. And our confidence level was 95%, so 0.95. Okay, so our confidence interval ends up being negative 0.009 to 0.048. And notice in here in the middle, what it's telling us is this is the confidence interval of p sub 1 minus p sub 2. Okay, so telling us that is p sub 1 minus p sub 2. So the idea behind these confidence intervals is that this is the interval in which we expect to find the difference between these two groups. Okay, so now we can talk about how to interpret this. So what would we expect? What would be the difference between two groups who were the same? So if two groups were the same, what would be the difference? And the answer is there wouldn't be one, right? There wouldn't be one. Which a difference of 0 mathematically, if there isn't one, would be 0. Okay, so the difference P1 minus P2 should equal 0. So the question is, if there isn't a difference between the two groups, if they're the same, we would expect 0 in this interval. So back to this problem, is 0 in the interval? And the answer to that is yes, because the left-hand bound is negative and the right-hand bound is positive, so 0 is between those two numbers. So what can we conclude based on that? Based on that, we can say there is not sufficient evidence to suggest a difference in the proportion of men and women with at least one tattoo. Okay, so because 0's in this interval, the evidence is suggesting that there is not a difference. There is not sufficient evidence to say there is a difference. If 0 wasn't in the interval, then we could say there is sufficient evidence to suggest there is a difference. So at this point, why don't you guys pause the video and try doing the same idea for this second problem. Okay, so now that you've all had a chance to try this one, let's go ahead and talk about it together. So the body mass index of an individual is one measure that is used to judge whether an individual is overweight or not. A BMI between 20 and 25 indicates that one is at normal weight. In a survey of 250 men and 250 women, the Gallup organization found that 203 men and 207 women were normal weight. Construct a 90% confidence interval to gauge whether there's a difference in the proportion of men and women who are a normal weight. Interpret the interval. Okay, so we've got our two groups here are men and women. For X, we get 203 for men, and N is 750. For women, X is 270, and N is 750. Okay. And so now we can go ahead and use the calculator to do our confidence interval. So we want to do a 2 prop Z int. So TPZI, and then we had 203 out of 750 for our first group, 270 out of 750 for our second group, and 0.9 as our confidence level. So our confidence interval in this case is negative 0.129 to negative 0.050. So is 0 in this interval, meaning that the groups would be the same? No. So is 0 in the interval? And the answer to that is no, because we go from a negative to a negative, and there's no way for 0 to be between two negative numbers. Right? So 0 is not in the interval, so that means there is sufficient evidence to suggest a difference in the proportions of men and women who are normal weight. Okay. Whoops, sorry, I just wrote that all out without you guys being able to see it on the camera. So here's what I wrote down while I was talking over it. Okay, so there is sufficient evidence. Okay. So that's it for this time. Thank you for watching this lecture video. Next time we'll be back with section 11.2, which is about doing the same idea for means, except with dependent samples. So in the last one in this section we talked about independent samples. In the next one we'll talk about means and dependent samples. So that's it for this video. Thanks for watching. Make sure you're doing all your assignments. And as always, if you have any questions, feel free to send me an email or a remind message, and I'll get back to you as soon as possible.